In this lecture, we'll get to talk a little bit about chemistry, which we've already seen, so this should be a review. We're going to talk about atoms, elements, compounds, those things, and chemical bonds. The water supporting qualities will come just a little bit later. So we need an essential question, as we usually do. And this one's just going to be, what are atoms and compounds? And compounds. And then we want, and how are they formed? Because we want to know how they're formed. How are they formed? You probably already know this, so this will be a good review for you. If you didn't quite get some of those things, then maybe it's a good time to go back over it. So let's go. Elements, atoms, and compounds. So living organisms are composed of matter. That's just anything that really takes up space, so has volume and mass. Okay. Or we could think about weight, though we'll know that's a little different later, but really it has volume and mass. So volume and mass. Matter is composed of chemical elements, and we know those are substances that can't be broken down into any other substances by chemical means. Okay. So it's kind of the purest of things. So, pure. There are 92 elements that occur in nature, but only a few exist in kind of a pure state. Usually they exist with other things. We do some chemical means to get them to where we can kind of tell that this is carbon or oxygen or whatever, because they usually kind of exist with other stuff. Well, except for carbon, I will take carbon back. Okay. These would be the elements that are the big ones. Okay, so these are kind of our major elements here. Oxygen, which we'll breathe, carbon, hydrogen, and nitrogen probably make up about 96% of our whole body weight. Okay, and that does include water. And then we have some things that we call, okay, I'm getting ahead of myself. But we have some other smaller quantities of elements: calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium. You'll see a lot of these kind of referenced in food products. But then there's the trace elements, and they're only 0.01% of the body weight, and that's boron and chromium, cobalt, copper, zinc, silicon, some other things that we need. So a compound is a substance consisting of two or more different elements in a fixed ratio. It's always a fixed ratio. And you could tell that by, let's look at H2O. You know, it's a compound of sorts, and it's a fixed ratio. Every time there's two oxygen, or we'll see if we get the words out today. Every time there's one oxygen, there's always two hydrogens attached to it. That's a fixed ratio. You can't have three hydrogens attached. That messes things up. It doesn't work properly. So it's always one oxygen to two hydrogen. Compounds are more common than pure elements. Things just like to sort out a little bit. Okay. Sodium chloride, so our table salt, is a common example of a compound in equal parts. So there's always one sodium to one chlorine. Okay. So you take sodium, which is a really cool thing. Again, this is one worth looking up. Sodium reacting with water. It's a really soft metal that you can cut with a butter knife. Chlorine is this really just toxic gas that's yellow in color and just nasty. And you put these two vile, horrible substances together and you get something delicious and magical. I don't know how it works. It's magic, and no, I'm just kidding. But chemistry has its own little magic associated with it. We take two awful, awful things and make something really delicious and kind of necessary. So about 25 elements are essential for human life. 4 elements make up 96% of the body weight of living organisms. That's what we just looked at. That's the oxygen, carbon, hydrogen, nitrogen. For some reason, we've come up with CHON over the years. Carbon, hydrogen, oxygen, nitrogen. Slightly different association, but those guys alone still make up 96% of your body weight. Fascinating. Trace elements really are essential but only needed in minute quantities. Quantities. They are essential. We absolutely have to have them, but just in teeny tiny little quantities. So an example is like some trace elements are required to prevent disease. You have to have iron because your body can't transport the oxygen without it. That's when when you're low in iron, that's the thing they call anemia. Okay, it gets to be a little harder to breathe and transport that oxygen around. Iodine deficiency prevents um, production of thyroid hormones, and it results in this thing called goiter, which there'll be kind of a mass at the thyroid that develops because we're not getting the proper hormones made. Fluoride's usually added to municipal water, and that helps with dental products and may reduce tooth decay. Um, this is kind of something we know of, but I've actually seen research that suggests that this may or may not be necessary. But that's science. It's always changing a little bit. So this is what we did know before, and if it changes, things will get updated. Okay? Fluoride is also in toothpaste, so you don't swallow it. You don't swallow the toothpaste after you used it most of the time. But just brushing the teeth applies fluoride, and you get what you need from that one. Several chemicals are added to food to help preserve it, or make it more nutritious, or make it look better. So if we look at the nutritional facts on labels and the drinks that you purchase, you can see some of the things that we're looking for. Like, look at some of the stuff here. We're talking about sodium and potassium, carbohydrates and proteins and stuff. Those and fats we'll talk about a little bit later. But even these guys are added, and some of them are trace elements like copper and zinc. Okay. And then the iron. So it lets you know if you're getting the daily value of those trace elements that you need. So it's a handy bit of information. Each atom consists, or it's going to be fun with words today. Let's just make it happen. So each element consists of one kind of atom. This is how you can tell that this is produced during the first week of school, is I don't have the language thing all smoothed out. So bear with me. We're going to make it work. All right. An atom is the smallest unit of matter that it still retains the properties of that atom. Element. See, case in point. It's going to be fun. All right, 3 subatomic particles in atoms are relevant to our discussion. Those are protons, electrons, and neutrons. Hopefully this is a reminder for you. Protons are happy and positive, electrons are negative, and neutrons are neutral. Usually that's represented with more of like an O, but I gave you the face just because. So neutrons and protons are packed into the nucleus of the atom. So you usually see it represented like we'll have a proton and the dark parts are the positive ones, and then we also have the neutrons in there. So we can make more. Well, or not. That's what happens when I don't have a stylus. So if we have 3 protons, 3 neutrons, we have a whole kind of nucleus there with 6 things in it. The electrons orbit the nucleus. I give you the horrible looking thing. This should have 2. Okay, making carbon. The negative, that's not even true. I don't know where my brain is at. The negative charge of electrons and the positive charge of the protons keep electrons near the nucleus. So because it's positive here, this I know I'll get correct. You know this. I feel like I'm allowed to make little goof ups here as I talk about it because you should know to be able to correct it. We'll get one freebie for this one, and then I'll be on my A game, I promise. So the electrons around the outside are negative, the protons are positively charged, and that gives them just a little bit of an attraction to each other. We'll go through this quickly and then I'll mention a break time, but the number of protons is the atomic number. Okay? And we usually see that. So number of protons, if I was making the one last time, it was actually had 3 little protons there. That should technically be lithium. So 3 protons, that's our atomic number. The mass number is the sum of the number of protons and neutrons in the nucleus. So what that last one would have been, that crazy picture I tried to draw with 1, 2, it's messing me up, 1, 2, 3 protons, 1, 2, 3 neutrons, that would be a mass number of 6. But what we actually have listed on there is the atomic mass, which I got from the internet, and it says 6.94 is the atomic mass, and it's equal to the mass number for the most part. Okay, it's supposed to represent an average of all the naturally occurring ones. So there'll actually be some 3 neutron ones, but it looks like there'll be more like 4 neutrons. Okay, so this is that atomic mass. And I am going quickly because I know you guys have had either chemistry or IPC, but if you don't feel like you understand it, come see me. Let's go, over the areas that you don't understand a little bit better. And I usually go a lot slower through this section, but I'm going quicker because I know you've had it. So if you need help, ask. Okay, so here's what we're looking at again. In the nucleus, those are the protons. These are the neutrons. So this guy has a mass number of 4. The atomic number from the 2 protons would be 2. So that thing technically should be helium. We could look that up by the periodic table. The electrons on the outside are 2. Ta-da. Okay. And it kind of forms a cloud, because the electrons don't actually contribute to the mass, because they're kind of like a poof. They're so fast moving and so small that they don't actually contribute mass to this. It's like a cloud around it. All right. So although all atoms of an element have the same atomic number, some differ in mass number. Okay. This would probably be a good place for you to pause. I like to mention moments where you should pause and take a break. Like we've gone for 11 minutes, so this is a good time to take a break, go get a snack, do something else, pause the video, and then come back. Maybe you are working through some C notes, maybe you write some questions out to the side. So think about it. All right, so different isotopes of an element have the same number of protons, but differ in the number of neutrons. Okay, that's what I was getting at with the little lithium guy earlier. So different isotopes of an element have actually behave identically in chemical reactions. So they do the same thing. I think I saw some, hydrogen normally doesn't have one, but there's one isotope where they made with 1 electron. No, I'm getting this wrong. Okay, hold on. It has 1 proton, 1 electron, but there's the other one where it has 1 neutron, and it doesn't normally have that. So there's some scientists, I'll have to see if I can find the video, but they made water with this kind of isotope of hydrogen, and then tried to see if they could make ice cubes sink. So if you couldn't follow that, don't worry about it. It's not necessary. If you could, it's a pretty cool thing. Just made me think about that one. There are radioactive isotopes, which I'll show you one of my favorite little videos on that. The nucleus will decay spontaneously and give off particles and energy. They're just not stable. It's usually for ones where the mass gets so big in the nucleus that it just can't hold itself together anymore. Okay, so here's examples of carbon. Carbon-14 gets used a lot, but normally there's carbon-12 and it's got 6 protons and 6 neutrons, so that gives it a mass number of 12. Sometimes it has 7 neutrons and giving it a mass number of 13. And a lot of what we see and we use in kind of parts of carbon dating is the 8 neutron variety that gives it a mass number of 14, which we appropriately call carbon-14. Living cells can't distinguish between isotopes of the same element because we've got a neutral particle in there. Can't really tell. So radioactive compounds and metabolic processes can act as tracers, because if we can use some that glow but our body can't distinguish it, then we can kind of follow it around. The body just takes it in like, oh, it's the same thing I normally have. But we've kind of labeled it a little bit differently so we can detect it with some instruments. And so using these instruments, we can kind of use these radioactive tracers to monitor living organisms. That's actually kind of how we get towards PET scans. So radioactive tracers are frequently used for medical diagnoses. Sophisticated imaging instruments are used to detect them. So we've got the positron emission tomography, and that's the PET scan. It can tell us where those injected radioactive materials are. The PET scan is useful for diagnosing heart disorders in cancer and brain research. Okay. A lot of the PET scans are used in staging of cancers. So once they identify, they do a biopsy and discover that it is a cancer, then they can use a PET scan to determine where it's gone to. Okay, so here's a healthy person and one with Alzheimer's patients. So you can see that they put these tracers in here to see what's going on with the brain activity. And we get some really interesting images this way. In addition to the benefits, there are also some dangers associated with radioactive substances. Uncontrolled exposure can cause damage to some of the molecules in a living cell, especially to DNA, which we'll talk about later, leading to mutations, which have some possible negative side effects. Whereas if chemical bonds are broken by the emitted energy, which causes abnormal bonds to form. So there are some potential for harm there. Okay. Now we're going to talk about chemical bonds. And I like chemical bonds. They're fun for me. The only way I ever learned chemical bonds was talking about relationship type things, like we make little atoms friends. We're not friends, so we're going to talk about those. If you have a different way that you've learned, use that. Okay, whatever it is that makes you get the information. So on 3 of the 3 subatomic particles, protons, neutrons, and electrons, to review, only electrons are directly involved in chemical activity of an atom. So only electrons. They're the outermost thing. So the thing on the outside is what makes it react. Okay, it's like, if they're on the outside, they're the things that are going to bump into each other first. So that kind of makes them the thing that does the chemical bonding, or is responsible for it. Electrons can be located in different electron shells with different characteristic distances from the nucleus. An atom may have 1, 2, or more electron shells depending on how large that atom is. Information about the distribution of electrons is found in the periodic table of elements. Periodic table is just a well done thing. It's beautifully designed. Okay, so we go back, we could look at this one. This should obviously be, we got 1, 2, 3, 4, 5, 6. So this would be carbon. Right, we notice the different shells. So we've got 6 here, right? Or we've got 2 here in this inner shell and then 4 on the outside. Right? And so we'll know that we want to, in this outer shell, make 8. Follow that octet rule. But what you can see is the first shell here is in this first kind of row. We get 1 and 2. And our second shell, which is the second one on the outside, we want to have a total of 8. So you can see it increasing 1, 2, 3, 4, 5, 6, 7, and 8. It made an indication of where I was there. And the third shell, same thing applies, and we need 8 in that one. So there's 1 here, 1, 2, 1, 2, 3 here, 1, 2, 3, and 4, all the way to 6, to 7. I can't count apparently. 5, 6, 7, and 8. I skipped a number. And we're always looking to get 8, because this is kind of where an atom wants to be at. The number of electrons in the outermost shell is called the valence shell. So it's the outermost is the valence shell. It determines the chemical properties of the atom. Again, the thing on the very outermost part is the thing that's going to bump into something else. So that's kind of the thing that does the reacting the most. Atoms whose outer shells are not full tend to interact with other atoms in ways that enable them to complete or fill their valence shells. And the first one's 2, so hydrogen's always trying to get 2. But then the second and third are 8 and 8. It gets a little challenging up higher, but that's usually where we tend to stay, as we want to get that octet rule and get to 8. When 2 atoms are incomplete, outer shells react. Each atom share or donate or receive electrons, or both partners end up with completed outer shells. So they've got to do different tactics in order to get complete and happy. These interactions usually result in atoms staying close together, held by attractions called chemical bonds. Okay. So that's them staying together. They are bonded together. A covalent. I like the way this is worded because valent is our outer shell. And if you think about like co-workers, cohabitate, it's together. So these are the ones that share because they have their outer shell together. So they share a pair of electrons. That's a covalent bond. And sharing is usually a tighter bond than anything else. When we talk about relationship stuff, if you share things, it's a stronger bond. If you share with your friend, you have a stronger bond than, would be with a give and take relationship, which is the other one. So two or more atoms held together by covalent bonds actually form a molecule. So that's kind of the separate thing there. A covalent bond connects two hydrogen atoms in a molecule of hydrogen gas. So each has one electron on the outside. Okay, and so when these two guys share together, they essentially both feel like they have two. Okay, this guy feels like he has two, and this guy feels like he has two. So everybody's kind of happy in that situation. Okay, I don't think the video will show. I'm happy to show those in class or make them available to you. They just never seem to click when we do these. Let's see, we can try it. No, it's not going to want to work. We'll try again later. So there are four alternative ways to represent common molecules. Hydrogen atoms are held together by a pair of shared electrons. And in oxygen, two oxygen formed two pairs of electrons, so they'll double bond, indicating a structural formula by paired lines. So you can see what that double bond would look here, and it's when we've got two, they'll look like 1, 2, 3, 4, 5, 6, 7, 8. Same with this oxygen. It feels like it has 1, 2, 3, 4, 5, 6, 7, 8. Same thing here is that the more I share, the stronger that bond is. So this one's going to be harder to break because sharing two sets is a lot stronger than sharing one set. We can also put it together. It's kind of like chemistry in this way is kind of like putting a puzzle together. It's like how many can I fit and what are the little rules. So in order to do that, it's, hydrogen needs to share so it can feel like it has two, and carbon needs to feel like it has 8, so it can form 4 covalent bonds. These guys are usually nonpolar. It's not, we'll talk about polar in just a minute. The polar thing happens with water because it only needs to share with 2, but they kind of end up staying closer and those electrons stay somewhere else. It actually gives the oxygen a slightly negative charge and the hydrogen a slightly positive charge. So that's something we'll get in with the properties of water a little later. So hydrogen and oxygen are molecules composed of only one type of element, but methane, CH4, and water are compounds with 2 or more different elements. So they've got those. But again, compounds because it's still a fixed ratio. Okay, we'll talk about this one, but this would be another good place to take a little break, chunk your notes, go grab a snack. Now, I can be paused, unlike in class, but I can be paused here. So go take a break. All right, so atoms are covalently bonded molecules continually compete for shared electrons. So the attraction or the pull of shared electrons is called electronegativity. More electronegative atoms will pull harder. The way I like to think of electronegativity is it's kind of a lot about how attractive is that atom. Some atoms are a lot more attractive, and so they end up kind of being a little, needier on here. We'll look at it. Molecules of the same element will pull towards each atom equally because each atom has its same electronegativity. They're equally attractive, so they're going to share equally. Nobody's better than another one. They're equal. The bonds formed are called nonpolar covalent bonds. There's no polarity. There's no sides here. Water has atoms with different electronegativity, so oxygen attracts the shared electrons more strongly than hydrogen. Oxygen actually tends to be a bit more pretty than hydrogen, so it's going to take just a little bit more. I don't know, maybe it's not attractiveness or just neediness, I'm not sure, but it takes it a little bit more often. It takes those electrons more often than the hydrogen does. So the shared electrons spend more time near the oxygen. So that oxygen then has a slightly negative charge because the electrons are negative, and the hydrogen atoms have a slightly positive charge because, they're getting it from their protons. This is what's called a polar covalent bond because there are sides or poles. They're positive, negative ends. We might end after this. We'll see how far we can get. But an ion is an atom with an electrical charge resulting from the gain or loss of one or more electrons. So if an electron, that negative thing, is lost, then we have a positive. If the negative kind of electron is gained, we're adding a negative, then we have a negative charge. Two ions with opposite charges attract each other. So positives and negatives will always attract each other. And when this attraction holds ions together, it's an ionic bond. And a salt is a kind of ionic compound. Any kind of salt. Okay. And we'll look at this animation a little later. But this is actually results from completely different electronegativities. The chlorine is very, very attractive. Think about it. Like, this one's super attractive. I'll put it on here. It's like super attractive and really kind of, let's think about like ugly. If you think about a situation where you see a really attractive person with a not so attractive person, what do you think is happening there? It probably means the unattractive one has money. So think of the electrons as money. It will give the attractive one its electron, its money, to keep that bond together. So, well, I don't need that little extra. And the chlorine's going to be happy to take it, and that bonds them together. It's not as strong as a bond as the sharing type stuff, but it works. Okay. And these guys form kind of this like lattice structure where it's like one after another. There's the positives and negatives kind of towards each other. Let's see, we can talk about this one just briefly, but in living organisms, most of the strong chemical bonds are covalent. Sharing is just a stronger bond than giving and taking, which is what an ionic bond is. We can go back to that, but the ionic bond is in fact a give and take relationship. One of them has to give something up and the other one has to take it. So it has to give that up and this one has to take it. Okay. Crucial to the functioning of the cell are weaker bonds between molecules. And these things, one of the most important types that we're going to talk about is called a hydrogen bond. And it's between water molecules. This will be our last little bit here, but the hydrogen atoms of a water molecule are attached to the oxygen parts of the polar covalent bond. So remember, we said the oxygen was slightly negative, right? Because it just is a little bit needier. And these are a little bit more positive. So when you have several water molecules together, I'm going to write all over the screen just because I can. Oops, I did it wrong too. These actually wouldn't happen. So these two positives wouldn't attract, so this doesn't work. What actually would have to happen is we'd have to have another water molecule this way, and notice the slightly negative charge would be attracted to this slightly positive charge. So these two guys should be attracted together. That one you may not know of, and it's a weird one, but we're going to talk about that one. We'll do some activities. So, because of this weird V-shape, water's polar, and it's got unequal distribution of charges. The partial positive charge allows each hydrogen to be attracted to a nearby atom that has a partial negative charge. So with my ugly picture, we'll look at a better one in just a second. Weak hydrogen bonds form between water molecules, so between different water molecules. Each hydrogen bond of water can form a hydrogen bond with a partially negative oxygen. So it's always hydrogen to oxygens. I'm going to put it's a dotted line type thing because it's not an actual bond, it's just an attraction. The negative oxygen pole can form hydrogen bonds with two hydrogen atoms. So it's the negative of this one, and the positive of this one, and they sort of have this interaction. So water molecules can hydrogen bond with as many as 4 partners. And it's not, again, a video, but this is what it looks like. So there's 2 negative ends on the oxygen, and they can attract to the hydrogens. That's what the white part is. That's the hydrogen, and this is the oxygen. So with the positive hydrogen with the negative oxygen, and that positive hydrogen with this negative oxygen. So they can form kind of 4 hydrogen bonds for each. We'll go through that in a little bit more detail a little later. Just remember that the structure of atoms and molecules determines the way they behave. Atoms combine to form molecules. Hydrogen and oxygen react to form water. So these are reactants because they're reacting together, and these are the products because they're what's produced. Okay, there you go. Chemical reaction, the reactants are H2 and O2. They're converted into oxygen, or there it is, the words again. Water, that's the product. So chemical reactions don't create or destroy matter, they only rearrange it. Okay. Again, I know I'm going very quickly here, but I know you guys have seen some of this stuff before. So 2 hydrogens with 1 oxygen, 2 hydrogens with the other oxygen. So nothing is gained or lost here, it's only rearranged. Okay. Okay, let's maybe come back to that. I'm happy to kind of stop here, and we'll look at kind of the rest of that reaction bit a little bit later. So I know I moved through some of that quickly, but again, as you go through it, if you find that there's areas that you don't know or don't understand, send me an email or come by tutoring and let's talk about it and make sure that you get those components and that foundation to chemistry, because we're going to need it, especially this semester with some of the energy stuff. Okay? So make sure that you've taken your notes and you're good to go. And if you have any questions, email me.